Welcome to The Explainer. Today, we're playing tech detectives to uncover the brilliant little hacks that allow modern AI to actually read human language. Seriously, if you've ever wondered how large language models can seamlessly process everything from complex Shakespearean poetry to the weirdest new internet slang, you are in exactly the right place. We're going to trace this whole fascinating evolution, starting from the early days of basic word vectors all the way up to the advanced subword tokens running today's absolute best systems. Let's get into it.
So let's kick things off with the ultimate puzzle. How exactly does an AI process a brand new word? Say something like Dogecoin, or a phrase that is totally Zoomer approved. Human language is incredibly messy and fluid. We're constantly inventing new proper nouns, mashing words together, making up slang literally every day. And for us humans, well, context usually gives away the meaning. But for a machine that relies on a fixed dictionary, a new word is just a brick wall.
And that brings us to the main villain of our story today, the OOV, or out-of-vocabulary word. In the early days of natural language processing, this villain completely broke language models. Imagine you're reading a book, but every single time you hit a word you don't explicitly know, your brain just completely shuts down and swaps in a blank space. That is exactly what happened with early foundational models like Word2Vec and GloVe. They just had absolutely no story for words they hadn't explicitly seen during their training. To understand how we actually defeated this OOV villain, we first need to look at Section 1, Beyond Word2Vec's Limits. Back then, Word2Vec was completely revolutionary. It used this iterative approach to train one embedding per word. But at the exact same time, there was another parallel line of research looking at something called matrix factorization. And researchers were looking at these two entirely different approaches and wondering, was Word2Vec's step-by-step approach fundamentally better, or was the difference just an artifact of how these two distinct methods crunched word counts? The field really needed a definitive answer to move forward. And that question was decisively answered in Section 2, GloVe, or factorizing the matrix. GloVe proved that matrix factorization was a profoundly effective path forward. The core concept here relies on a massive co-occurrence matrix. It's basically a giant table asking, okay, how often does word J appear in the immediate context window around word I? The goal is to train vectors so that their mathematical dot product actually matches the real-world probability of those words showing up together. By directly factorizing this matrix with a really clever mathematical goal, researchers proved it didn't just match Word2Vec, it often beat it, and it cost way less to train. Now here is GloVe's real secret sauce. Think about it. If you just count how often words appear together, words like the and are going to absolutely dominate the math, right? They're everywhere. So GloVe uses a specific weighting function to dial down those ultra-frequent pairs, so they don't overpower the whole system. Plus, they used a brilliant trick. They calculated both a center table and a context table of weights, and the final word embedding is just the sum of both. Summing them together reliably outperforms using just a single table. It was a huge win. But that brings us to Section 3, the unknown word problem. Because despite GloVe's incredible efficiency, it still crashed hard when it met our villain. Yet neither Word2Vec nor GloVe had any solution for completely unseen words. If a word wasn't explicitly locked into their fixed dictionary, the model was totally blind. And think about the sheer volume of language for a second. Zoomer approved, Dogecoin, any random proper noun coined last Tuesday on Twitter, even every grammatical variation of a rare root word. You just can't pre-train a model on every conceivable variation of every word in human existence. The vocabulary would be, well, impossibly huge. Enter Section 4, FastText, or the sum of its parts, which tackle this problem with a brilliant total paradigm shift, treating words like Lego bricks. FastText realized that a word isn't just a solid, unchangeable block. It's actually the sum of its character engrams, essentially smaller, bite-sized chunks of letters. Look at how FastText completely deconstructs the word where. It breaks it down into pieces of, say, 3 to 6 characters. So you get WH, WHE, HER, ERE, alongside the full word itself. FastText embeds all of these individual little pieces. And the final vector for the word where, it's just the mathematical sum of all those component vectors added together. The absolute genius of this is how it behaves when the model encounters the unknown. Let's say the AI sees the word whereupon for the very first time. Under GloVe, instant failure. But FastText looks at whereupon and goes, wait a minute, I recognize WH, I know HER, I've seen where. Because they share so many of the same familiar n-gram Lego bricks, this totally unseen word gets a perfectly sensible vector that lands right near similar known words.
It's incredibly resilient, especially for bad spelling and highly complex languages.
FastText was a massive leap, for sure, but it eventually led to Section 5, BPE, and the Transformer Revolution, because once transformers arrived, the whole game changed. Even resilient word-level vocabularies capped out at around 1 million entries, and that simply wasn't enough for the open-ended, infinite nature of real language generation. To scale up to the massive AI models we use today, researchers adopted Byte-Pair Encoding, or BPE. And it works like this. You start with a baseline vocabulary of just individual bytes or characters. Then you scan your massive text corpus and count every single adjacent pair. You find the most frequent pair, let's say it's T and H, and you merge them into a brand new single token TH. And then you just repeat over and over. Real tokenizers learn between 30,000 and 100,000 of these merges. By the end, frequent sequences like ing or the become single tokens, while rear words are just broken down into familiar, previously merged pieces. This guarantees that literally any text can be tokenized. The OOV villain, permanently defeated.
This brings us to a monumental shift in the tech landscape. Honestly, that quote really says it all. Subword tokenization is the undisputed standard today. Whether you're looking at the word piece variant used for BERTs, sentence piece used for models like Llama, or the byte-level BPE that starts with 256 raw bytes used by the GPT models, they all completely rely on this fundamental concept.
Okay, let's wrap this up with Section 6, choosing your embedding tool. Because knowing the history is awesome, but knowing what to actually use when you're building your own data science projects, that's the real superpower.
Consider this your ultimate cheat sheet. If you just need pre-trained general-purpose word vectors and you aren't expecting weird vocabulary, grab a 300-dimensional GloVe model. It's super efficient. But if you do expect misspellings or newly coined slang, definitely pick FastText so it can piece things together. Building a production text classifier with a simple linear model? The classic TF-IDF is still your best friend. Now, if you are feeding anything into a transformer, absolutely never swap its tokenizer. Always use what the model shipped with. And lastly, if you're ambitious enough to train a language model entirely from scratch, your literal first step has to be training a BPE or sentence piece tokenizer on your dataset.
So what's the big takeaway from all of this? Overcoming the limits of AI language wasn't about simply forcing a machine to memorize a bigger dictionary. It was a complete philosophical shift. We had to teach AI to recognize the fundamental building blocks of language itself. By shifting from whole words to character engrams and eventually down to subword tokens, we gave AI the flexibility to process language as fluidly and dynamically as we do. I'll leave you with this provocative thought to chew on. We've optimized language for machine ingestion absolutely perfectly, but it really begs the question, what gets lost in translation when poetry, emotion, and human nuance are reduced entirely to the mathematical frequency of adjacent bytes? Thank you so much for exploring the fascinating evolution of AI embeddings with me today. Keep learning, keep questioning. I'll see you in the next explainer.